One thing that's often useful is this idea of a misadjustment ratio. If, for example, we had excess mean squared error that was much smaller than the minimum mean squared error, then it doesn't really matter. If, on the other hand, that very same excess mean squared error was much larger than the minimum mean squared error, that might be an important thing. So we'll look at misadjustment to be the ratio of those two. Ideally, this ratio would be 0, with the excess mean squared error being 0 and divided by the minimum mean squared error. So recall that the minimum mean squared error is sigma v squared, as we defined in our last lecture, where v is the uncancelable, unpredictable noise or part of d. And so we can write this then using our expression for the misadjustment error, or the excess error from last time, which was mu, our adaptation factor, times sigma v squared, which we now know is E min, times the trace of our autocorrelation matrix over this denominator, as you see. And we'll divide that by v squared, or sigma v squared. So those will cancel out, giving us just another expression here, mu times the sum of all the eigenvalues of Rx. We could have just left that as the trace of Rx if those two are equivalent. But looks like a nice simple equation there. But let's go ahead and write that this way too, where we get mu trace of Rx over 2 minus mu times the trace of Rx. So two expressions, they're identical, but just written different ways. And this is our misadjustment ratio. So the first thing you'll notice is that, as before, if mu was very, very small, then this will reduce down to 0 over 2. And the misadjustment ratio then goes to 0, which is what we'd like. If mu is very large, then this goes to 1. But we have to be careful making that type of assumption or analysis, because we got these equations based on the assumption that mu was sufficiently small. So if mu is not sufficiently small, these approximations aren't very good approximations anyway. But in fact, if mu isn't small enough, our filters will diverge, and the misadjustment ratio is going to be potentially infinite. Back to the other side, if mu is sufficiently small, that mu times the trace of Rx is much less than 2, then this all simplifies to this expression, which once again is the same as this one. So if we choose mu to be some constant beta times 2 over the trace of Rx, then for this situation, we're going to get that mu is approximately equal to, well, beta, or m. The misadjustment ratio is approximately equal to beta. So we can decide what is appropriate. And once again, this is actually a really nice way of working things, because beta is now a quantity that's more, I guess, universal, more fixed. If we can deal with the misadjustment ratio of about 1/2 or maybe 10%, then we just choose beta accordingly. And remember, these are approximations. The 1/2 probably isn't going to work. The trace of Rx may be very large. But as long as, actually I misspoke. As long as beta is in the range of say 1/10, then this approximation is reasonable, a reasonable approximation to make. And so I usually use this beta factor. And we'll talk about that in the next lecture when we talk about the normalized LMS algorithm, which now comes up with, once again, something based on this beta factor to choose a mu, but it approximates the trace of Rx. And the fact that it approximates this shouldn't come as a surprise. We've been approximating things left and right as we've proceeded with our development here. So let's look at a little example. Suppose we have a input of length 2, so we have two eigenvalues. One is 20, the other is 1.5. So the trace of this is going to be about 21. So 2 over the trace is approximately 0.1, so I'll just use 0.1 in this example. What happens when we approximate this? Well, m actually should have come out to be 0.1346 for the 0.1, and for beta is equal to 0.01, we get m is 0.011. So those two approximations are pretty good. In this case, I would say that it works there, but you can see that if we went too much larger than 0.1, it may not. What happens if we go up to 0.5? Well, in this case, 0.5, we do not meet our convergence conditions.